In our last video, we showed how to synthesize alcohols through reduction of ketones and aldehydes. And the reducing agents we used were lithium aluminum hydride and sodium borohydride. And it was a pretty straightforward reaction, right? With our hydride attacking a carbonyl. Here's a hydride attacking a carbonyl. Electrons coming out to form a negatively charged alkoxide intermediate. And that alkoxide intermediate can become protonated to give us our final alcohol. Now, there's a little twist on this reaction that happens when we use a hydride source like lithium aluminum hydride to reduce carboxylic acids and esters. So let's talk a little bit about that twist. Okay. Now, really, this alkoxide intermediate is very important in this reaction. And there's different destinies of this alkoxide intermediate. Now, previously we talked about, well, the only destiny is it becomes protonated to form an alcohol. But there's a second destiny that might occur on molecules that have a potential leaving group on this carbon. Okay. Aldehydes and ketones don't really have a leaving group. We got a carbon group here, a carbon group here. For a ketone, those aren't just going to leave as negatively charged carbons. Or if we're an aldehyde, we might have a hydrogen here. It's not going to really leave as a hydride. But when we deal with functional groups like carboxylic acids and esters, we do have potential leaving groups. And so there's a second destiny that might occur with these alkoxide intermediates, and that's for it to reform the carbonyl and kick out a leaving group. So let's look at one of these mechanisms to illustrate what's going on. But I want you at this point to think about this alkoxide intermediate and think of that negatively charged oxygen as sort of like a light bulb. That light bulb is there to remind you what or could this alkoxide reform the carbonyl? Is there a leaving group or not? So remember, this is our light bulb, and we'll see this as we talk about the mechanisms of this reaction. So let's look at a reaction of a carboxylic acid. Let's just put a simple one up here. How about acetic acid maybe? Whoop. Here's my carbon, CH3. Okay, carboxylic acids and esters have to be reduced by lithium aluminum hydride, which is more reactive. They're not effectively reduced by sodium borohydride. But the mechanism is the same as what we saw before. We've got a source of hydride, this reducing agent. It will attack the partial positive charge on the carbon, kick these electrons out to form our alkoxide intermediate. And remember, this negatively charged alkoxide intermediate should remind us to think of something, right? Boink, our light bulb. Now, the question to ask when you see the light bulb is, can these electrons come back in to reform the carbonyl? The only way they're going to come back in to form that double bond is if something else leaves. Aldehydes and ketones, we didn't have any good leaving groups. Carboxylic acids and esters, we have potential leaving groups. If you think about a carboxylic acid, this could leave as OH, but we know OH minus isn't a very good leaving group, but it can be made into a good leaving group through protonation. Okay. So in the presence of acid, we can reform this carbonyl and kick out water as our leaving group. We need that acid in there in order to turn that weak leaving group of OH minus into a good leaving group of water. So what we've done here is a one-step reduction, right? We have reduced the very oxidized carboxylic acid, reduced it not all the way to an alcohol yet, but we've reduced it to an aldehyde. Okay. Now, if we repeat this application of lithium aluminum hydride, this hydride will be able to react with this aldehyde, just like we saw in the previous video. So by reforming this carbonyl, we've also reestablished this nice partial positive on the carbon, which is attracted to the negatively charged hydride. And so we can go through a second round of reduction to reduce the aldehyde to a second alkoxide anion. Again, we see this negatively charged alkoxide. We should say, whoa, light bulb, can I reform this carbonyl? And in this case, the answer is no. We don't have a good leaving group here, here, or there. And so the next step upon the addition of acid would just be protonation of the alkoxide to form our final primary alcohol. Okay. So with carboxylic acids and esters, it's important to remember two things, right? One, you have to use the more potent lithium aluminum hydride as your reactive hydride source. And two, we're going to reform our carbonyl group. And that's going to lead to a two-step reduction process. To give us our final, really, primary alcohol. We could do this reaction also with esters. Let's look at esters. Let's take asymmetrical ester here. React it with our hydride source. To form our first alkoxide intermediate. Here's our new carbon-hydrogen bond. And we recognize that alkoxide, boing, we have to think, can that carbonyl reform? In this case, it can. We have a potential leaving group here. This would be an ethoxide leaving group, which kind of like OH minus isn't a very good leaving group. It's a good nucleophile. But in the presence of acid, H plus, instead of a bad ethoxide leaving group, we can kick out, really, ethanol as a leaving group. Okay, we've reformed that carbonyl. Reduced our carboxylic acid, or our ester that we had at the beginning, to an aldehyde. And in the presence of our hydride source, we'll do our second round of reduction. Here's our second alkoxide. This is just like the last video when we were reducing aldehydes. We have another carbon-hydrogen bond. Here's our alkoxide. Light bulb. Can this reform to form a carbonyl? No, we don't have any good leaving groups here. And so instead of reforming that carbonyl in the presence of acid, we will just protonate it to form our final primary alcohol. Okay, in this case, our leaving group was ethanol. Our final product is ethanol. So you might expect from this reduction of this ester, we might just make a bunch of ethanol. If this was a different leaving group, we would get two different primary alcohols, right? If I didn't have this carbon here and this was CH3, I would lose methanol and then form ethanol at the end. So sometimes you get a mixed combination of primary alcohols at the end by reduction of esters.